Here in video lecture 6.3, I hope to provide a rather brief history of the last 500 million years of tectonic movement on Earth's surface. And as you recall, the last 500 million years, although impressive amount of changes have occurred, that's rather small compared to the entire history of 4.54 billion years that Earth has been around. We're going to be looking at a series of maps that have tried to reconstruct the geography of various plates and land masses over time. And so 500 million years ago, we have the Cambrian Period. What we're looking at, if we see this vertical line right down the middle, that's this vertical straight line, that's the prime meridian. Going horizontal right down the middle, that's the equator. So the crosshairs where those two meet, where those two cross, is right there in the center of this map here. And we'll note that actually all the land masses and continents are actually in the southern hemisphere, which is much different than what we see today, in which most of the continents and land masses are actually in the northern hemisphere. Like I said, it's very hard to predict exactly where all these land masses were 500 million years ago, but some have argued that what we're looking at right here 500 million years ago is the breakup of a former supercontinent. Going down more recently, we have the Ordovician Period. We can see the continents have moved a bit more. One thing to note is this is the origins of the Appalachian Mountains, actually right about this period here. So the Appalachian Mountains are one of the oldest mountain chains that we actually find today on Earth's surface. Just left of center in this Silurian period, 420 million years ago, we can see the collision that created the Atlas Mountains and the Appalachian Mountains. And so essentially what we have is we have two large land masses that have now since collided with each other, creating those chains of mountains that I described in a previous discussion. Now moving on to Devonian Period. Here the yellow star indicates the location of where Indiana is. And so one of the things we'll know is the Indiana was actually way far down in the southern hemisphere. And so one of the things to note is over time, Indiana in North America has moved up into the left in this image here. If you ever wished Indiana was more closer to the beach, well, you would have to go way back in time to this period here. And so the yellow star indicates now that Indiana was actually rather close to the coastline. And then soon after, well, relatively soon after, Indiana actually was no longer close to the beach. In fact, it was underwater in a shallow sea, which is going to be critical to understanding our bedrock here in a minute. But one of the things to also note is we see more vegetation being added across the surface. This, of course, wasn't added by human beings. This is over time evolution. You see the introduction of plant species. Then 300 million years ago, we have the Carboniferous Period. One thing to know is you have that massive ice sheet there in the southern hemisphere. Key to understanding that is that massive ice sheet is critical to understanding why we see more land being exposed. Essentially what that means is water is no longer being held in the oceans. Instead, it's being held on land as ice. And so one of the things to know is when the world has these glacier periods in which we have these massive glaciers across our surface, what that does is that decreases, that lowers the sea level. And essentially when that lowers the sea level, more land is now exposed, which explains why in this image here we can see a whole lot more land being exposed than the previous images. One thing to note is where Indiana is here is right there along the equator. And so Indiana actually used to be right underneath that intertropical convergence zone, right underneath that equatorial low pressure trough. And this is going to be critical to understanding where all this coal comes from in Indiana, which I'll explain a little bit later. Now moving to the Permian Period, 250 million years ago, we can see here Pangaea. Here we have the one massive supercontinent across the world. Here's the Triassic Period. I like to showcase this because it builds on those previous global pressure belts that we mentioned beforehand. And so that yellow star, that's where Indiana is. We see it's right there on the equator. One thing to know is along the equator you can see this green belt, this dense vegetation. Well, what caused that dense vegetation? What caused that green belt? The equatorial low pressure trough, the ITCZ, which has always been around. It's been around for a good amount of time. So it's not a deal where it's just, the last 100 years that we've seen these various pressure belts. Further, if we look to the north and the south of that yellow star, you see drier areas. Those drier areas illustrate, once again, the subtropical high pressure belt that exists both north and south of that equatorial low pressure trough. Now Indiana is moving further to the north and to the west, closer to its present-day position. And now we see the beginnings of the Atlantic Ocean. So the yellow star indicates where Indiana is, but one thing to note is Africa and North America and South America, they're all about ready to break up and break off of each other. That Atlantic Ocean continues to get wider, and so the Atlantic Ocean is actually getting wider over time. It's separating further and further and further. So the distance from Africa and North America is increasing over time, albeit at very, 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 very slow rates. By 150 million years ago, during the Jurassic Period, we can see further separation of the continents of North America, Africa, and Europe as the Atlantic Ocean continues to separate. One thing to note is South America, Africa, Antarctica, Australia, today what is the Indian subcontinent, are actually all there together, for the most part there in the southern hemisphere. So we continue to move through these maps. Now I want you to focus in on this island in the red circle. That island in the red circle is what is today India. By 100 million years ago, we can see that much of the Great Plains in the southeast United States, or what is today those areas, was actually underwater in a very shallow sea. We can see Indiana and its location there. Further, if we look down the bottom in the red circle, we can see now that the Indian subcontinent has further moved away from its previous location. We can also see the formation of our good friend Madagascar. So Madagascar, an island just off the coast of Africa, and the Indian subcontinent essentially were one piece way back when that have since separated due to divergent plates and plate separation that's occurred there. Which becomes even more clearly evident as we look at this map here as the Indian subcontinent and Madagascar further separate from each other, as the Indian subcontinent makes its voyage in the Indian Ocean as it makes this direct beeline for a head-on collision with Asia. We look over at North America, we can see now North America, much of it is above sea level in this period here. By 50 million years ago, we can see that separation there in the Atlantic Ocean continued to separate as North America, Africa, Europe further separate from each other. Further in the red circle, we can see the Indian subcontinent colliding with the Asian landmass, and this is the origins of the Himalayan mountains. If we look over in the southeastern part of the map, over in the bottom right, we can see Australia has started to break off fully from Antarctica and is heading towards its present-day position that we see there in the South Pacific Ocean. By 10 million years ago, we see the glaciers now starting to form again. So global temperatures were going down, and the North Pole and the South Pole started to have water stored on land instead of being in water. And so what would that do? That was going to cause sea levels to go down. So as sea levels go down, it reveals more continents. What this did then was it revealed these land bridges that then connected North America and South America. And we can see that land bridge that is today Central America, or the Isthmus of Panama as it's referred to. Further, that land bridge across the Aleutian Islands, there it connects Alaska to Russia, was also revealed. So during this time period, 10 million years ago, temperatures started to go down. So much that by 2.5 million years ago, actually this area of Indiana was underneath a massive glacier. And so we can see this glacier actually came further down from its North Pole and its South Pole locations, essentially illustrating the fact that we had an extreme drop in global temperatures during this million period of years. One of the things to know is we're going to come back a little bit later on in this glacial period during the Quaternary period is absolutely critical for understanding why Indiana looks the way it does today. Finally, we have reached the end, the Holocene period. One thing you'll note, comparing this to the previous map, is Florida. Florida is actually skinnier. Why is Florida skinnier? Well, it's because the glaciers that dominated during that previous period, the Quaternary period, have since melted. So we can see there's still, of course, some white there at the top and the bottom, but much less than what we saw in the previous image. And so what that's going to do is it's going to cause global sea levels to actually rise, which is a key idea we'll come back to talk about when we talk about glaciers. This is the present time. What we see here is the Holocene period, the current snapshot of where our plates are. But like I've said before, they're continuing to move, and we're about 250 million years away from all these continents coming back together on the other side, forming a new supercontinent.